Hello everyone, this is Chemical Reaction Engineering Tutorial 5, Isothermal Reactor Design. In this tutorial we're going to learn two different questions. The first question is basically to determine whether the reactor is PFR, PBR or CSTR. And then in question number 2 we try to analyze a couple of questions related to isothermal reactor design. Let's start with question number 1. In this question, we're going to have a volumetric flow rate about 2500 gallon per hour of methacillin, and it's being isomerized to a mixture of orthosilane, methacillin, and parasilane. And we also have the information that the reactor has about 1000 feet cubic of catalyst. And then we have information of temperature and pressure, which is 750 degree Fahrenheit and 300 psig. And under this condition, we basically have 30% of the methacillin fed to the reactor is isomerized, which is basically the conversion is about 37%. And then we have another information if we run the reactor at different flow rate, 1667 gallon per hour, we're going to have a conversion about 50%, which is higher at the same temperature and same pressure. So the question is, for part A, we need to find out the type of reactor used, and we need to show the calculation to prove the answer. And then in part B, if we need to build a second plant that is bigger, using volumetric flow rate of about 5500 gallon per hour, the same temperature and the same pressure. Now we need to calculate what's going to be the size of reactor based on volume of catalyst required to have a conversion. In the new plant, it's about 46% instead of 37% in the previous condition. In order to solve the problem, we need to list all the information that we have: volumetric, the two types of the reaction, the volume of catalyst, and also the first condition, which is volumetric flow rate about 2500, and the second condition is about 1667 gallon per hour with the conversion about 50%. So in order to find out the type of the reactor, since we know that this is flow reactor, so it's going to be either CSTR with catalyst or a PBR with catalyst. And then based on the rate law, we can write down, for example, methacillin goes to parasilane, we're going to have rate constant K1. And then for methacillin to orthosilane, we're going to have K2 as a rate constant. So if we write down the rate law for both reaction, we're going to have K1 times concentration of M plus K2 multiplied by concentration of M. And then if we combine the rate constant, we can just have K multiplied by Cm. And from stoichiometry, we can break it down. The rate law of Rm is going to be K times Cm naught 1 minus the conversion. So in case 1, we're going to have a volumetric flow rate about 2500 gallon per hour, and the conversion is about 37%. And then in case 2, we're going to have volumetric flow rate about 1667 gallon per hour with the conversion about 50%. So in order to find the reactor, we need to find the condition. Since this is the same reactor that we use, what it means that the volume of the catalyst at case 1 should be the same with the volume of catalyst in the case 2. And we also know that since both reaction is been done at the same temperature and pressure, then the rate constant for K, which is K at the case 1, it's going to be the same with the rate constant at case 2. So if we multiply these two, we should have the same number. So now we need to find out whether it's CSTR or PBR. So we assume if the reactor is CSTR, then we're going to calculate W, which is based on the mole balance equation. It's going to be Fm0 multiplied by X over the rate law. And if we break it down, we're going to have at the end the volumetric flow rate multiplied by the conversion over K multiplied by 1 minus the conversion. So if we plug in the number for case 1, the volume of catalyst is going to be 2500, which is the volumetric flow rate, multiplied by the conversion 37% over K, we don't know yet, and then multiplied by 1 minus 0.37. It's going to be equal to 1468.25 over K. And then in case 2, if we calculate the W, we're going to have 1667 multiplied by 50% conversion over K multiplied by 1 minus 0.5. We're going to have about 1667 over K. So based on this calculation, we can see that W1 and W2 has this different number. So what it means that the reactor is not CSTR. So now we try to calculate if the reactor is PBR. Then W, based on the mole balance, is going to be equal to the integration of Fm0 multiplied by dx over rate law from 0 to x. And then if we integrate that one based on the rate law that we have, we're going to have W equal to minus V0 volumetric flow rate multiplied by logarithmic natural 1 minus conversion over K. And then if we plug in the number for case 1, W is going to be equal to minus 2500, which is the volumetric flow rate, multiplied by logarithmic natural 1 minus 0.37 over K. We end up with the value of 1155.09 over K. And then for case 2, if we plug in the number, we're going to have W equal to minus 1667 ln 1 minus 0.5 over K, and we'll end up with the number very close, which is 1155.47 over K. So what it means that W1 equal to W2 for the PBR case. So we conclude that the reactor is PBR reactor. Now let's try to solve the part B of the question. So in part B, we need to find the reactor size for a new volumetric flow rate, which is 5500 gallon per hour, and new conversion, which is 46%. So since we know that the reactor is PBR, then we can right away calculate the size or the volume of catalyst W equal to minus volumetric flow rate over K multiplied by logarithmic natural 1 minus conversion. Since we don't have the K information, then we need to find out the K first using the data from case 1, which is a volumetric flow rate of 2500 with the volume of catalyst about 1000 cubic feet. So K, it's going to be equal to minus V0 over W multiplied by logarithmic natural 1 minus X, which is rearranging from this equation. So if we plug in the number, we end up with K equal to 1.155 gallon per feet cubic hour. And now we can easily calculate the W, which is new W, is going to be equal to minus 5500 logarithmic natural 1 minus 0.46 over K, which is 1.155. We end up with the volume of catalyst about 2934.22, which is much bigger than the volume of catalyst in case 1 and case 2. So now let's move to the question 2, which is multiple choice question. So in part A, we have in a reversible liquid phase second order reaction. The reaction is A goes to product with 50% conversion in a PFR operating isothermally, isobarically, and at the steady state. The question is, what conversion would be obtained if the PFR operated at the half of the original pressure with all else unchanged? So based on this question, we can easily see that the previous conversion, the original conversion, is 50% conversion. So the question is, what happens if we change the pressure? So we need to analyze all the information that we have from the question. And in the first couple of information that we have, we see that the reaction is basically in liquid phase. And from what we'll learn, we know that if we have liquid phase, then the pressure effect is negligible. So we can say that if we run this reactor at different pressure, we're basically going to have the same conversion than the previous one, which is 50%. Now let's move to the part B of the question. In part B, we have a reaction, irreversible, heterogeneously catalyzed gas phase second order reaction, and we also have information that the rate constant is 0.234, which is determined from experimental data. However, it says that the experimental data failed to include the larger pressure drop in the reactor in his analysis. So if the pressure drop were properly accounted for, what's going to be the real rate constant? So in this question, we need to find the correct K. So if we have the reaction A goes to P, which is second order, we're going to have the rate law is going to be equal to K times Ca squared. And if we're breaking it down based on stoichiometry, we end up having of rate law of K multiplied by Ca naught squared multiplied by 1 minus x squared multiplied by W, so multiplied by y squared, where y is actually the pressure change, P over P naught. So we know that the rate law is proportional to K multiplied by y squared. And we know since the pressure change, y squared is going to be less than 1. So the K that we found previously, which is 0.24, 0.234, is actually the real rate constant multiplied by the pressure. So if we try to account the real, we have to calculate the real K, which is account for pressure change, then the K real is going to be equal to the K previously over y squared. So if we plug in the number, we're going to have 0.234 over y squared. And since we know the y squared is less than 1, then the K real is going to be bigger than 0.234. Now let's continue to the question 2, part C. In this question we have elementary isomerization exothermic reaction. A goes to B and its catalyzed reaction is carried out isothermally at 400 K in a PBR, which pressure drop plays a role, with alpha equal to 0.01 per kilogram, and we have 50% conversion. And we also have information that the equilibrium constant at this temperature is 3.0. And if we know the mass flow rate m, and if the particle diameter is increased by a factor of 4, what's gonna be the new conversion? So we need to analyze the problem. Since we have the new particle diameter, which is 4 times the previous particle diameter, we need to find the formula that include the particle diameter. So we know that alpha is actually related to beta, and then beta itself related to a particle diameter. So what it means that from these two equations we can see that alpha is inversely proportional to particle diameter. And then we can conclude that if we increase particle diameter, it's going to decrease the alpha, and the other way around, it's going to increase the conversion. So we can answer that the new conversion is going to be bigger than 0.5. So now let's go to the last part of the question, which is part D. We're going to have the elementary isomerization exothermic reaction, and then we have all data exactly the same with the previous one. We have temperature, we have alpha, 50% conversion, mass flow rate m, but the question is what's gonna be the equilibrium conversion. In order to solve this question, we need to derive the rate law of this reaction. So we have reversible reaction A goes to B, then we're gonna have the rate law equal to minus K1 times Ca plus K negative 1 times Cb. And then we know that this is an equilibrium condition, so we can have Kc equal to Cb at equilibrium over Ca at equilibrium. And if we break it down based on stoichiometry, Kc is going to be equal to the equilibrium conversion over 1 minus equilibrium conversion. And if we rearrange the equation, we can have equilibrium conversion equal to Kc over 1 plus Kc. So since we know that the Kc is 3.0, and we can plug in the numbers to find equilibrium conversion, which is 3 over 1 plus 3 equal to 0.75.